So today we're going to do space math, the final frontier. And it all comes from tangent lines and the Pythagorean theorem. So cool, so awesome. Our number 17, how far into the ocean can you see if you're standing on the beach? So let's say that your eyes are 6 feet above the ground. We are wanting to know how far we can see into the ocean. So what is our line of sight here going to be in feet? So first thing we need to realize is that when we're standing on the Earth is round, and we have the radius of the Earth, which is 6,400 kilometers. Now we have a problem because we're doing 6 feet and kilometers, and so we have to do some conversions, and that's what's going to make this math kind of suck. But honestly, it's not that bad when we have our calculator. So let's do it, and I'll pull up my calculator here so we can do that all together. So this is a right triangle because we're dealing with tangent lines, so it's basically just an application of the Pythagorean theorem. We're starting small with just standing on the beach, but we're going to get big, like space big, final frontier. It's going to be awesome. All right, so we have our Pythagorean theorem. We have our leg of 6,400, that's our a squared, plus our b squared, which is the x squared, that's the distance that we're looking for, the other leg. Then our hypotenuse is going to be the radius of the Earth of 6,400 plus whatever our height is here. So if we fill in those values, the only thing we have to convert the 6 feet into meters before we can add it together with the 6,400. So I'm going to take my conversion factor, which is 1 foot is that many meters. So in my calculator, I'm going to do 6 times 0.3048, and that's going to tell me how many meters I have. Now this is still not kilometers, this is meters, so technically we would divide that by 1,000, but I'm going to put it in as a decimal. So I have 6,400 kilometers, 0.0001, and there's the meters that are going to be there. All right, so here's my Pythagorean theorem. I know it looks ridiculous, but it's actually just fine. So all we have to do now is subtract the 6,400 squared from both sides. So in the calculator, what I'm going to do is 6,400 0.001828. I'm going to square that, then subtract 6,400 squared. All right, now that's going to give me the difference between those two squared. Now remember, that's going to be what x squared, our distance squared, is equal to. Now I don't want the distance squared, I want just the distance. So what I have to do is take the square root of both sides. So in the calculator, I'll take the square root of that. So caret 0.5. Okay, and that's going to tell me how many kilometers I can see. So if you are 6 feet, if your eyes are 6 feet above sea level, which means you're at the beach, right? That means you can see 4.838 kilometers. Now, for all of you Americans out there, which is us, isn't that obvious? We need to convert that to miles. So what I'm going to do for that is another conversion factor by multiplying the kilometers times 0.6214. And that's going to convert it to miles for me. So we'll be using those conversion factors quite a bit. So we can actually see 3 miles into the ocean, at least this distance, not technically that distance. We would have to do a little bit more math. It's doable, but we're not going to do that in this video, okay? To see how far we can actually see along the curved surface of the Earth, not the as the crow flies or the straight distance there. All right, so what we're doing here basically is the Pythagorean theorem. Here's our Earth. We have a radius of 6,400 kilometers. Whatever height is what we're going to be adding to our hypotenuse length of the radius, right? And then that's going to give us a distance. And so we can derive this formula by subtracting the 6,400, this, from both sides. So we take the hypotenuse minus this side squared, and that's going to give us the distance squared. So that's pretty much the formula we're going to be using. Well, the only different thing is I might take the square root of this to get the distance, and that's kind of like the distance formula there. And then using these conversion factors. So for 18, instead of standing on the beach, we're actually going to go 16 feet up into a life tower. So this exact same math, the only difference is now we are going to convert that again. So I'm going to take 16 and convert it to, by multiplying it by 0.3048. I'm going to convert that into meters, and then I'm going to do 6,400 0.004878. Okay, and I'm going to take that value squared, and then I'm going to subtract from it 6,400 squared. Okay, and that's going to give me the square kilometers. So essentially we're at this part here. And then all I have to do is take the square root of both sides, and that's going to give me the kilometers, and then multiply it by the conversion factor to change it to miles, which will give me 4.9 miles. So whenever we were standing on the beach, we could see 3 miles, but now that we're up in this Lifeguard Tower, we can see 4.9 miles. So we can't see further, but maybe not as much further as you thought that you could, unfortunately. All right, so let's go even higher. Instead of 16 feet, let's go to the Lighthouse of Alexandria. So Alexandria was a trading port in Egypt. This is actually like the birthplace of you could say like geometry kind of all came together in this place. They had a bunch of they had a library and university there. The library got burnt down famously, but this is where Euclid of Alexandria, obviously, where he came together and kind of brought together from the teachings of geometry from the Greeks before that and other sources, and put together all of the geometry from the time and formed his Elements, which is the oldest book and the most printed book, or the second most printed book besides only the Bible, which is actually kind of cool. We talked about that at the beginning of the year. So anyway, this is their lighthouse that they use. Of course, it's massive. So I kind of did some extrapolation and estimated that we thought it was about 450 feet above sea level. Now they claim that you could see the light from this lighthouse from 100 miles away. And we're going to test that claim. So if we know how high it is, how far into the ocean can we see 100 miles from this distance? Well, let's test it out. So we're going to do our height here. We need to convert it from 450 feet to kilometers. So what I'm going to do is 450 times our conversion factor of 0.3048. Okay, and that's going to tell me how many kilometers. So 64, or how many meters? 13716. Okay, and I'm going to take that squared, again, just like before, minus 6,400 squared. All right, and then I need to take the square root of that. If you notice, we're just following the same pattern. All right, so that means that we can see 41.9 kilometers. When we convert that to miles, we'll get 26.04 miles. So they claimed you could see the light from 100 miles away, a ship could, but they actually could only see it from 26.04 miles away. So then the question might follow, how high would the tower have to be, a lighthouse, in order to be able to see it from 100 miles away? Not like that's necessary at all, but now our math is going to be a little bit different. So what I need to do is convert the miles to kilometers, or rather I think meters. So anyway, I'm going to do 100, and then I'm going to divide that instead by our conversion factor. Yeah, so going basically from miles back to kilometers. So I need to divide it by 0.6214. Okay, and that's going to give me, basically it's the 161 kilometers that I have here. Okay, so I have my radius of the Earth plus the distance that we need to be able to see the other leg, and that's going to give me the hypotenuse that I need. Now remember, the hypotenuse is the height plus the radius of the Earth, so we'll subtract the radius of the Earth when we're done. So let me put this in the calculator real quick. So we have 6,400 squared plus 161 squared. All right, and then remember I got to take the square root of that, so I will. And notice this is just going to be 2.02 kilometers above the 6,400 that we started out with the radius of the Earth. So essentially what we know when we take the square root of all that, which we did, is that we would get 2.023 kilometers essentially, and if I change that to feet, that's going to be 6,637 feet. Now there are 5,280 feet in a mile, so this is actually over a mile tall. So the question is, certainly that's a lot less than the Lighthouse of Alexandria. So to put this into perspective, these are the tallest buildings that exist at the making of this video, or when I Googled this or whatever. And so I think it's the Burj Khalifa, which is in Dubai, which is in the UAE, United Arab Emirates. It's the tallest tower, or the tallest building that I believe exists. And so that is, I think, like 830 meters, and we need it to be 2.02 kilometers. So you must be this tall to be able to see a lighthouse, or the light from it, from 100 miles away. And none of those buildings are anywhere near that, unfortunately. So sad. And if you're wondering, down there, that's actually our lighthouse. That's how tall it would be on the scale, unfortunately. The 161 meters. Yeah, 161, about right there. So nowhere near that. Could the smoke from the lighthouse have risen that high and you could see the smoke from 100 miles away? Perhaps, but my goodness, their math was way off. They should know better for being the birthplace of geometry. All right, so let's go even higher than that. The tallest building, let's go to Mount Everest. How far can we see from Mount Everest? So Mount Everest is 8.85 kilometers. So we're going to do 6,400, 8.85, and we're going to square that. And then just like before, we're going to subtract 6,400 squared from it. And then when we're done, we're going to take the square root. It's just the same algorithm over and over again. So that's how many kilometers we can see, and then we can convert it to 209 miles. Now there's going to be a bunch of terrain in the way, but let's imagine that the Mount Everest was like right by the ocean, and then how far could we see into the ocean? Because that should be pretty flat minus the tides, you know, and stuff like that. Then technically we'd be able to see 209 miles, but Mount Everest is not by the ocean, so you're going to have some terrain in the way. Kind of cool. What about the next highest thing that I could think of? The International Space Station. Because why stop? Why stop at Mount Everest? I mean, there's just numbers, right? So we're going to do the same thing. So that's going to be 6,400 plus 350. All right, so obviously it's that value. We're going to square it, minus 6,400 squared. Alrighty, and then we're going to take the square root when we're done, as we were doing before, and that tells us that's how many kilometers we could see. So the International Space Station, which is orbiting the Earth, is only 350 kilometers. Now that is not to scale here. So if I actually put it where it would be to scale, then what would we actually be able to see is right here. So it's actually orbiting, if this is the Earth to scale, that's how close the International Space Station, which is technically, I suppose, in space, that's how close it is orbiting to the Earth. I bet you didn't realize that, but you thought it was much further out there, right? And if you look at pictures from the International Space Station, that's their field of view. That's how far they can see, which is about a third of the radius of the Earth. So if you see the radius of the Earth, that should be about a third of it. And of course, you can see in both directions, right? So that distance is about the width of the Gulf of Mexico, I believe. So about twice the width of Texas. So let me show you some photos from the International Space Station, and you probably didn't realize they were that close. I mean, they're like, boom, or the Earth's right in their face. They were that close to the Earth. So here's a photo from the International Space Station. You probably recognize that country, the boot. That is Italy. And you can see, you can't see, you can't even see the other side of, you can't see England, you can't see the other side of Germany, or the coast there. It's like right in your face. So there's a good amount of time. I don't know how fast they're orbiting. I could figure that out. You could actually figure that out with physics, fairly simple, based on the gravitational pull. And so what would their, how fast would they have to be orbiting? But there's a good amount of time when all they see is just the ocean. So when they cross over the ocean, that because they're so close to the Earth, they just see ocean, 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 and then finally, oh, it's a country. What country is it? And you can imagine there's quite a lot of times when they don't see, when they're just seeing a landmass, whenever they're over a large continent, and they might not know, what they're looking at, which is kind of cool, really cool. Feels like we just like orbited the Earth on the ISS, but we didn't. I'm still alone in my room. But this is fun. Let's keep going. So here's another photo from the International Space Station. Again, all you can see is about the width of the Gulf of Mexico, or twice the width of Texas, but you've got a lot of clouds, so that doesn't really help. And in fact, we can only see about 20.6% of half of the Earth, because we would only be able to see half the Earth at any point in space, and so we can only see 20.6% of half of the Earth's surface, which is pretty cool. So what if we wanted to see a quarter or half of one side of the world? So if we could see half of the world, this half, and we want to see a quarter of the whole Earth, or half of the world, how far would we have to be back? Now what's fascinating about answering that question is we can actually do it with special right triangles. What? So this whole 1, 1, radical 2 thing that you taught me, I can use that and apply that to figure out how far I would have to be away from the Earth in orbit in order to see half of the world, which is a fourth of the world at any given time, like all the way from Antarctica to the equator. That's absolutely fascinating. So the question that I'm going to ask is, if we have a leg of 1 going to a leg here of 6,400 kilometers, what was my scale factor? Literally the radius of the Earth. The scale factor is the radius of the Earth, which is massive. Okay, so then what's this distance here? That's how high we have to be. Well, that's actually a simple calculation, because the entire length, the hypotenuse, is radical 2. So we have radical 2, and then I'm going to subtract radical 2. I'm going to subtract 1 from it, because if I take the radius away from that, the radius was 1, right? So radical 2 minus 1. And then remember, this all needs to be scaled up by a scale factor. So that's this length of the green part here, but it needs to be scaled up by my scale factor of 6,400. So that value times 6,400, which will give me how high I would have to be, which is 2,651 kilometers. above the Earth's surface in order to see half of the Earth. And this little blue line, by the way, that's where the International Space Station is orbiting. So they're orbiting here. They would have to slow down in order to orbit how much further away? Well, if I divided that by 350, because that's where they're at, so they would have to be 7.6 times further away from the Earth's surface in order to go from seeing 20.6% of the Earth to half of the Earth, which is fascinating. And the real question would be, is how much slower would they have to be at an orbit? Because the reason they're so close, and they want to be so close, is probably so that they can observe the Earth in orbit and have a faster period or a faster orbit. But if they were further away, they would have to be going much slower. Otherwise, they would fall out of space or fall into space, however you want to think of it. So, physics. Good. So you should take physics next year if you haven't signed up for it. It's how the world works. It's how all of it works. And geometry, apparently. So the next question we have is, what about the moon? So the next furthest thing from the International Space Station that is out there that I know of right now is the moon. So the moon is this many kilometers away from the surface of the Earth. So the question is, what percent of the Earth do you think you could see from the moon? Well, this sounds pretty impossible, but it's actually very doable if you see what I have going here. So this length here is going to be one of my legs. This is I have a right triangle here. So this is a right angle. Let me get out my pen so we can label that. This is a right angle because it is a tangent line. Okay. And then I have a leg here. This is another leg, which is actually the distance, and which we don't need to worry about that part, but we do have the hypotenuse here. So if I know the distance that we are, if I add that to the radius, that would be the hypotenuse, and then the leg is going to be the opposite leg, by the way, or depending on what theta I'm using, that would be the adjacent leg. So I have the adjacent leg and the hypotenuse, which is related by the cosine. If I take the cosine inverse of those two, that should give me this theta, which that theta is there. So that's 89.06%. That's going to be this angle that's being swept out. Now, if I wanted to know what percent of the measurement of the arc, so 180 degrees would be the full amount of half the Earth that I could see. So if I double this, because it's going to be on both sides, and then divide it by 180, that will give me the percent of half of the Earth that I can see from the moon, which would be 98.96% of half of the Earth. So by the time we get all the way to the moon, we can almost see almost all of half, right? There's, a little bit more than 1% of it that we can't see, but let's be honest, it's going to be maybe the Coca-Cola penguins or the polar bears. I think it's going to be okay. By the way, this is not to scale, because the actual distance, in order for you to be able to see like the Earth and the moon, we'd have to make this distance 10 times as long. So if you can imagine that going 10 times, 1, 2, 3, off of this page, it's going to be absolutely massive. So really, really far away. That's why it takes so long to get to the moon. How long did it take? I don't know. We should look this stuff up. Aren't you curious? That's what Google's for. All right, so from the moon, here's a photo, and here's the Earth. That's how far away we are, and that's the percent of half the Earth that we can see. So we can almost see everything. We can see all of Africa, see into Europe, and almost see the North Pole. And if the curvature of the moon was not in the way, then we'd be able to see the bottom part too, which is kind of cool. So here is another photo that we want to investigate. Now we're space investigators, which sounds epic, right? All right, and so the Apollo 17 mission, they were on their way to the moon, and they turned around obviously before they got to the moon, and they were taking photos of this beautiful blue marble. And this is the name of this photo. It's a very famous photo, and it's called the blue marble. So the question is, can we kind of like triangulate how far above the Earth's surface they were when they took this photo? So looking at the only thing in the photo that I can see and recognize, obviously, this is Africa, which Africa is about 8,000 kilometers in height, and difference between the latitude, lines of latitude there. So just did some math or whatever, you got it. And then, so if that's 8,000 kilometers, I can probably go another 8,000 here to the other side of what looks like Antarctica on the bottom. And then I can go a little bit further there, so maybe a little bit more than 16,000 miles. So I'm going to estimate about 18,000 kilometers is our field of view of the Earth. Now from that, I can do just kind of a reverse process of the last thing I did in order to find out how far away they are. Let's do this. This is gonna be awesome. All right, so in green here we have the 18,000. So imagine Africa, and then we got up here and a little bit on the bottom there. So that's 18,000. And then I want to find out, what is this theta. So what I have to do is find out what is 18,000 kilometers as a ratio of the circumference of the Earth. So the circumference of the Earth is 2 pi times the radius of 6,400 kilometers, which is actually not that bad. Like, it sounds really scary, but let's just do 2, and I think pi is right here. So 2 pi times 6,400. That's the circumference of the Earth. How hard was that? I mean, we're talking about big things, but like the math, it works in a little and it works in a big. So why not go big? Go big or go home. That's what I always say. I never say that, but if I was cool, I would. I just did. You're welcome. So I'm going to take that value and I'm going to divide it by that. And that's going to give me, oh, I forgot. I have to multiply that by 360. It's a good thing that was there. So take that, multiply by 360, and that will give me the theta. So I can see, let's see, go to 2. So 161.2 degrees. Now, if I divide that by 2, that will give me this theta, because that's the whole thing, and I want half of that, so 80.6. Now that I have 80.6, I can basically figure out this hypotenuse length of how far it is by kind of just doing the reverse of what I did. So I know the cosine of 80.6 is equal to the 6,400 over 6,400 plus x, where x kilometers is how far away they are. So if you remember, when x is on the denominator, what do we do? Well, we have that shortcut where we just switch these two, right? So that's all I'm going to do. I'm going to switch them, and then I'm going to subtract 6,400. I'm going to do it right in front of your face just to prove it. So am I in degree mode? I am in degree mode. That would be important. So I'm going to take that value divided by, so I'm going to do alpha x, divided by the cosine, so you can see exactly how it goes in, the cosine of 80.6. Did I do that right? Yeah. And then the only other thing I have to do is subtract 6,400 from that, because if you notice over here, I was adding that part there. So there we go. That's my estimate of how far they are from the Earth. Boom, it's right there. So what's really cool is they actually recorded how far they were when they took the photo. And the actual distance that they were was 29,000 kilometers. Now, we estimated 33,000 kilometers. So how close was our estimate? Well, here's a little comparison. And instead of 80.6 degrees, we actually had a field of view of half the Earth of 79.6 degrees, which is really close. And then when you doubled it, it was that. So absolutely amazing. And the estimate that we did of 18,000 at the very beginning, we should have actually done 17.779 kilometers, which is really sneaking close. So not bad, if you ask me. Not bad for just farting around, doing what we do, right? So if we want to see that in context, so I did scale it down now. So here's the Earth, there's the moon, very small compared to the Earth. You can look at their radiuses and compare them. If that's the total distance that they travel, they did less than 1/10 of that, more like 1/15 of that. So this is the distance that they actually traveled here, and there's their Apollo 17 or capsule, and so that's how far they had gotten away from the Earth before they turned around and took a photo of the Earth. So they had a very long journey ahead of them before they finally got to the moon. Now, what percent of the Earth can they see from the moon? I did that math for you, and didn't want to bore you with that, but it's the same thing we did with the other process. From the blue marble where they took the photo from the Apollo 17, they could see at that point 88.4% of half the Earth. So let's put all this together in one final grandiose shot. Here it is. So from the International Space Station, we can see 20.6% of half the Earth. That's at an elevation above sea level of, or an altitude, I suppose you could say, of 350 kilometers. Now, if you back up to the International, not the International Space Station, to Apollo 17, when they took the blue marble photo, this one right here, now we can see 88.4% of the Earth, but we have an elevation of 29,000 kilometers, which is way up there. But not really that far up there if you consider how far away the moon is, right? So then from the moon, now we can see 98.96%. Sounds like kills 99.99% of germs. It's kind of funny. But we have to go a distance of 384,400 kilometers from the moon, which is absolutely amazing. So we just did space math. Could we go even bigger? I don't know. What's bigger than this? The universe. But all of this, remember, is based on simple math. Trig, special right triangles, and the Pythagorean theorem. All this stuff we did in the last unit, and we just got to show off all that, and I am feeling really good. So I hope you guys are feeling good. Really cool stuff, like mind-blowing, so cool. I'm glad I got to make this video. Glad I got to update this video, because it was little bit slow paced the last time. But I'll see you guys later.